As was discussed in the electrostatics and magnetostatics modules, it is sometimes useful to express the electric and magnetic fields in terms of their potentials, rather than discussing them directly, to ease calculations. If you recall, we defined a vector magnetic potential, A, using this equation. The curl of A is by definition equal to B. A has no physical meaning apart from this. It's a completely made-up quantity that is only useful because if we find A, we can use it to find B. It turns out that we can also derive a wave equation for A. Watch this. If we take the curl of both sides of this definition and use Ampere's law to rewrite the curl of B in terms of the electric field, we get this equation. Now we have what we know will turn into a double spatial derivative of A on the left, but on the right we have the electric field, which we need to get in terms of A. So let's set that equation aside for a moment and go back to Faraday's law to get a relationship between E and A. Faraday's law gives a relationship between E and B, and we know that B is del cross A, so we can plug that in and then rearrange to show that del cross E plus dA dt is 0. Now, we might be tempted to say here that E plus dA dt is 0, but that wouldn't be valid. It's true that the curl of 0 is 0, but the curl of a gradient is also 0. So it's possible that E plus dA dt is not 0, but is instead equal to some non-zero irrotational field. So for the most general solution, we have to let E plus dA dt equal the gradient of a scalar field, which we'll call V, the electric scalar potential. Okay, so now we have a relationship between E and A, so let's go back to our wave equation problem. We can plug our new expression for the electric field in here to obtain this equation. This is in terms of the magnetic vector potential A, the scalar electric potential V, and the electric current density J. Now we're going to use a math trick. We said that the curl of A is equal to B, but we haven't specified the divergence of A. The curl and divergence of a field are linearly independent. It's like saying we specified the real part of A, but we haven't yet decided what the imaginary part is. Since the only part of A that we care about is the curl, because we can relate the curl to the magnetic field, we can let the divergence of A be whatever we want. In this case, it will make our lives easier to set the divergence of A equal to negative mu epsilon dV dt. This is called the Lorentz gauge condition. Once we plug that in, our wave equation for A becomes this. Del squared A equals mu epsilon d squared A dt squared minus mu J. Or in a source-free region, del squared A equals just mu epsilon d squared A dt squared. We can similarly obtain a wave equation for the scalar electric potential by taking the divergence of both sides of the equation we derived earlier, and then applying Gauss's law and the Lorentz gauge condition. If we do this, this is our wave equation for V with sources, and this is our wave equation for V in the absence of sources.